Greetings, physics enthusiasts. Welcome to AP Physics 1. No. Welcome to AP Physics 2. Yay! Unit 3, Lesson 4, where we will discuss electric potential. It's really one of my favorite topics, so I hope you enjoy this. Let's think not about electric stuff first. I want to talk to you about gravitational stuff for a few minutes. Because I think that's more concrete. You experience that every day and pay attention to it. And we're going to talk about gravitational potential. And then I'm going to use that as an analogy to explain to you electric potential. So gravitational potential. On Earth, one way of thinking about Earth is looking at it from far away. And we know there's this gravitational field that points toward Earth. In other words, Earth pulls stuff down. And of course, down is toward Earth. But another way of thinking about Earth is up close. What if you're in Nebraska where it's just flat? I've been in Nebraska. It's also beautiful. But anyway, and in Nebraska, up close, the gravitational field would look more like this. So these gravitational field lines up close end up looking parallel. And so I would say, that gravitational field is G. Gravitational field has the unit meters per second squared, which is equivalent to G is 9.8 meters per second squared. It causes that acceleration, but that's the same thing as 9.8 newtons per kilogram. Maybe that makes more sense. It's how hard the Earth pulls each kilogram of matter. And it just turns out that newtons per kilogram turns out to be an acceleration. Okay, all that to say, here is the gravitational field pulling stuff down on Earth. Now, let's go somewhere. Let's go into a room where there is a bookshelf. And there's an object sitting on top of that bookshelf. And maybe that object is going to fall off the bookshelf. It's potentially going to fall off of the bookshelf. So what does that mean? Well, that means that if it falls off the bookshelf, it's going to move down, 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 down. And while it moves down, Earth is going to pull it down. In other words, it's going to speed up. It's going to speed up on the way down, and its kinetic energy will increase on the way down because it's moving down and it's being pushed in that same direction. And whenever something is being pushed in the same direction as it's moving, we would say it speeds up. Another way of saying that is we would say its kinetic energy increases. If the opposite were happening, if it were moving one direction and being pushed the other direction, then it would be slowing down and its kinetic energy would decrease. But that's not what's happening here. Same direction, velocity and net force. Therefore, velocity will increase and kinetic energy will increase. Now, that's not happening right now. Right now, ain't nothing happening. But there is the potential for that to happen. So you want to talk about MGH. Pardon me. And we know that this has gravitational potential energy. In that sentence, potential is an adjective. Potential energy, MGH. And what we say is Earth is going to exert a force mg on it while it moves a distance h. So MGH is called gravitational potential energy, but it's the product of a force and a distance. Do you see it? Force times distance. And so you also might remember from chapter 5 last year in AP Physics 1, the work energy theorem. The work done is equal to the change in kinetic energy. And so the work is a force times a distance, and that's KE final minus KE initial. And in this case, the force exerted is mg, the distance is h. They're both in the same direction. The force and the displacement are in the same direction. So it doesn't matter that they're both negative because negative times negative is positive. And that equals KE final. minus KE initial, and it's at rest at the beginning. So the final kinetic energy is equal to mgh. So that should feel familiar from last year. Feel free to think through that more at length if you want. But I want to take this mgh, which is explicitly a force times a distance, and I want to think about it as m times gh. You learned in your math class that a times b times c equals a times b times c, even if we have parentheses around AB on the left and around BC on the right. You may or may not remember it, but this is called the associative property of multiplication. You don't need to know that. It's just fun to say, oh, that's why we need to know this. But this is force times distance. Great. But what I want to talk about today is this. The mass of the book is going to move through this distance h, and in that space there is this gravitational field g. So this is the mass it's going to fall, this is the gravitational field, this is h, the space the object is going to move through. And what I want to say is, I'm going to redraw it now with less clutter. What I want to say is this space right here is described by GH. I even used cursive to connect the G and the H together like it's one thing. GH describes the space. There's a gravitational field G in the space, and the space extends for a distance H. Now, the book sitting on top of the shelf, or the block, or whatever I said it was, might have a small mass, might have a large mass. So, a little bitty children's book might move through here and gain a small amount of kinetic energy, whereas a big unabridged dictionary with a large mass might move through this space and gain a larger amount of kinetic energy. Because remember, mgh is the amount of kinetic energy the thing gains when it moves through the space. So different objects might have different masses, but they all move through the space GH. So what I do is I describe the space with this phrase, GH, and I call GH gravitational potential. GH is gravitational potential. Now, first of all, when I say gravitational potential, you might be hearing gravitational potential energy. You might be supplying that third word. Don't supply it. In the phrase gravitational potential energy, energy is the noun, modified. What kind of energy? Gravitational potential energy. That's not what I'm saying here. I'm not being lazy and leaving off the third word. Potential is now a noun. Like, you have potential to go to college. You have potential to get a PhD in physics. Potential in that sentence is a noun, or those sentences. And potential here is a noun. It is a thing, not a modifier. So GH is gravitational potential. Let's examine this a little bit more, and then we'll move on to electric stuff. If mgh is gravitational potential energy, this whole thing, mgh, has the unit joules. Therefore, gh, well, I took out the mass part, and therefore gh has the unit is joules per kilogram. This has so I took out the kilogram part, therefore this unit is joules per kilogram. Just to prove that for you, what is a joule? You remember, joule is kilogram times meter squared over second squared. That's a joule per kilogram. A joule is kilogram times meter squared over second squared. Divide by kilograms. So now I get meter squared over second squared. Now, I said that's joules per kilogram. Well, obviously, there. But what is GH? Does GH really have the same unit as this? Well, G is an acceleration, meters per second squared, and H is a distance. Meters squared times seconds squared. That's the unit for this. And that's the same as joules per kilogram, meters squared per second squared. I would not think of it as meters squared per second squared. There's not a lot of meaning there. But what is the meaning of joules per kilogram? GH, this gravitational potential. Well, I have a bookshelf in my room that's about 2 meters tall. So if H is 2, and G is 9.8, which is about 10, it means that my bookshelf over there, like this, is 20 joules per kilogram. What does that mean? That means if a kilogram, a book with a mass of a kilogram, falls, its potential energy at the bottom will be 20 joules. If a 3 kilogram book falls, each of those kilograms gains 20 joules. So the 3 kilogram block will have a kinetic energy at the bottom of 60 joules. Each kilogram that falls through here gains 20 joules of energy. The space is 20 joules per kilogram. So that's all I need to say about that. Well, I'll say one more thing. What if I threw something upward? So I threw it up from the ground, and maybe it just barely rises to the top. Well, every kilogram that went through here was slowing down. So every kilogram that went up here lost 20 joules of energy. Maybe they still had energy left when they got to the top, so it's going to rise up even higher. But this space, if things move down through it, every kilogram gains 20 joules of energy. If things move up through it, every kilogram loses 20 joules of energy. The space is described by a gravitational potential, GH. Okay. So now let's talk about it in terms of electric stuff. So I'm going to change color from purple to green just to make it look different. Let's say I have an electric field that points this way. I have a uniform electric field, E, and I'm going to place a charged particle there. If I put a charged particle here, the electric field will push it in the direction of the electric field. And so if it's sitting here at rest and nobody else is pushing on it, this charged particle will move to the right and it'll go faster, faster, faster. It's as if it's falling this way to the right. How hard does it get pushed? Well, so the electric force, F sub E, electric force is EQ. I hope you remember that from last week. So the electric field times the amount of charge. So the force exerted on it is EQ. And the distance it's going to move, I'm going to call D. So just like over here, where I talked about as the object falls off the bookshelf, it gets pushed with a force mg and it moves the distance h. Force times distance is the work done on it. Well, now I'm going to say force times distance is the work done on the particle. So the change in kinetic energy of the particle is equal to the electric force times distance, which is equal to EQ, the electric force, times the distance. Now, just because it works, do you remember the commutative property of multiplication? A times B equals B times A. So I'm going to put the Q and the E in an opposite order. I'm going to write Q, E, D instead of EQD. And the reason I'm doing that is to make it look more like this MGH. I had the amount of stuff, field, distance. And now I have amount of stuff, field, distance. So I started here talking about force times distance. Now instead, I'm going to talk about Q times ED. Q is the amount of stuff, very much like the amount of mass. And ED actually describes this space. The space has an extent, a distance D, and it is filled with the field E. So ED describes, D-E-S-C-R-I-B-E-S, describes the space. In the same way that GH described the space there, or even more prettily here, GH described the field there, the field strength times the distance. ED describes the space here. And so I'm going to call ED, I'm going to define that as electric potential. Not electric potential energy. QED could be considered electric potential energy, but ED is the electric potential. That's the big thing. So electric potential is defined as ED. You can picture someone walking around with a baseball cap that says Ed. You know, your friend Ed is actually electric potential. Electric potential, your friend Ed. Anyway, what do you think the unit for electric potential is? Well, gravitational potential energy was in joules. So when I got rid of the M, the unit for GH was joules per kilogram. So if electric potential energy, if it's energy, its unit is joules. QED has the unit joules. So ED, I'm taking out the charge part, ED has the unit joules per coulomb. Very, very, very important. Electric potential describes the space. It has to do with the field in the space and how far the space extends. Electric potential is defined as ED. You can memorize it as electric potential, my friend Ed. And the unit for electric potential is joules per coulomb. So I'm going to cross out this little E right here and move it down there. So E is electric field in the unit newtons per coulomb. And then electric potential has the unit joules per coulomb. Notice that those units are different. This is the unit for electric field. This is the unit for electric potential. Electric field is abbreviated with the letter E. Ooh, I wonder what letter we use to abbreviate electric potential. So let's see, we've got electric. I'm going to summarize it here. Electric field, abbreviated with the letter E, and the unit is newtons per coulomb. Electric potential. Again, I don't mean electric potential energy. It's not that I'm being lazy. Electric potential is different from electric potential energy. Electric potential has a letter that we abbreviate it with, and it has the unit joules per coulomb. And the reason I keep avoiding this letter is it's just not very satisfying. You want electric potential to be P or something, right? It's not. The letter we use for electric potential is capital V. Electric potential abbreviated capital V. Now, the reason that we use capital V to abbreviate electric potential is that electric potential has kind of a nickname. There's something else we call it. I don't like this other word. I'm just going to tell you about it. It's used a lot. I don't like it because I think it obfuscates meaning. Everything here is what you need to know. But the other word for electric potential, voltage. You've heard about voltage and the number of volts on a battery. I'm trying to reach for a battery. I don't have a battery here, but you know what a battery looks like. So when it says 6 volts on a battery, joules per coulomb is abbreviated. You know how kilograms times meters over seconds squared is abbreviated with the Newton? So joules per coulomb is abbreviated with the volt. And sadly, both voltage and volt are abbreviated with a capital V. So if I want to say something like, the force is 6 newtons. Okay. But what if I want to say the voltage is 6 volts? That looks really weird because this V and this V don't mean the same thing. This V is the electric potential, and this V is the unit for electric potential. That's a terrible equation, and it leads to some misunderstandings. So I tend not to use the word voltage, and I tend not to use the unit volt. I talk about electric potential in joules per coulomb. That has more meaning for me. But if you do use these other words, voltage and volt, try to remember what they really mean. Okay, so that is the introduction to electric potential. Let me tell you a couple more things. You might have wondered about this electric field I drew, a nice uniform electric field. And you're like, well, how do I get an electric field like that? The way we get an electric field like that is we have a big plate, a sheet, and we fill it up with charge. And we have another big plate or sheet over here, and we fill it up with charge. If the field goes this way, or the field points this way, that's the direction positive charges would get pushed. In other words, this plate or sheet is positively charged, which would push positive charges to the right. And this one is negatively charged, which would pull those positive charges to the right. So the way we get a nice uniform electric field like this is with two sheets. So I can have, two sheets of paper like this, and I would hold them parallel to each other. And that would create this. And I'm setting you up for what we're going to talk about in the next video. In the next video, we're going to talk about what happens when I have two things like this. So I just wanted to set that up for you. It creates this nice, lovely, uniform electric field in the center. All right, there's one more thing I wanted to show you. I'm sorry, I'm looking at my notes and there's something weird on them. All right, the final thing I want to show you is, has to do with fun units. The electric field is expressed in newtons per coulomb. So it exerts a force on charged particles that depends on how charged they are. But there's another way of writing newtons per coulomb now. Newtons per coulomb is equivalent to volts per meter. Really? It doesn't. They don't look the same at all. But what is a volt? A volt is a joule per coulomb. That's the volt per meter. So then I have to divide by meters. A joule is a kilogram times meter squared over second squared per coulomb per meter. And do you see that this meter and one of these go away? And what is a kilogram times meter per second squared? That's a Newton. And I'm left with coulombs. So I've proven it to you that newtons per coulomb and volts per meter they are equivalent units. So sometimes electric field strength, they'll say, oh, the electric field E is, 7 newtons per coulomb. But sometimes they'll tell you the electric field strength in volts per meter. It's got to be the same number because a newton per coulomb is equivalent to a volt per meter. Be sure you make a note of that, highlight it. Newtons per coulomb and volts per meter are both units for field strength, electric field strength. That will be helpful for you in the future, I promise. Okie dokie, that's all I have for you today. Be careful out there. Don't break any of the laws of physics.